Hello, and welcome to the Blue Waters Overview. I'm Scott Lathrop with the Blue Waters Project at the National Center for Supercomputing Applications at the University of Illinois. It's my pleasure to welcome you today to hear from a number of staff at the Blue Waters Project. I'd like to begin by introducing Bill Kramer, the Principal Investigator for the Blue Waters Project. Bill.
Thank you, Scott. I'd also like to extend my welcome to everybody who's listening live, and also anybody who sees this presentation from asynchronously after it is finished. We are at Blue Waters very interested in expanding the types of use and the people who are using the system, and that's the purpose of the seminar today, to introduce Blue Waters to you, introduce some of the staff who are providing the services and making sure Blue Waters works excellently, and then to entice you to actually think about what types of science and research you could be doing and making use of Blue Waters. So again, welcome. Thank you for your time and patience, and we'll start with the presentations with Brett Bodie.
All right, I'm going to do a brief introduction to the overall project and the system, and then we'll turn it over to some others. So what is Blue Waters? Blue Waters is both a system and a project here at the National Center for Supercomputing Applications. Blue Waters is funded by the National Science Foundation, similar to Exceed Resources, but we have somewhat different goals than does Exceed. Certainly, we share in common the goal to deliver top flight computational resources to computational scientists nationwide to enable them to do state-of-the-art simulations of their research. Our goal goes a little bit beyond what Exceed does. Exceed delivers resources to many different projects around the country. Our goal is to take the very high end of those users and deliver resources that are just not available anywhere else. So we deliver resources at a scale to computational science teams that allows them to move their science forward an order of magnitude beyond what can, or more beyond what can be done elsewhere. So what does that mean? So we're really the capability system within the National Science Foundation's portfolio. So instead of delivering computational resources to thousands of users and hundreds and thousands of projects, we deliver resources primarily to the NSF community to only 30 to 40 projects at a time. That enables them to get a very large computational resource and allocation on that computational resource to really move their science forward. Blue Waters itself is a system that's one of the most capable in the world. It was certainly in the top 5 systems in the world when it was deployed 5 years ago, and is still in the top 5 for many different aspects of its capability. For example, it's still at 1.6 petabytes of memory in the system. It's still perhaps the largest HPC system in the world. It still has one of the fastest file systems in the world, even though it's 5 years old, at delivering a sustained performance over 1 terabyte per second. It's one of the largest tape systems in the world, at capable of more than 250 petabytes of storage. And we have one of the fastest external network connectivities in the world, with more than 400 gigabits per second of network connectivity. So even though we're 5 years old, it's still one of the largest and most capable systems in the world. The Blue Waters project is more than just the system. We build upon the system itself and the National PETASCALE compute facility that it's housed in, but we add on to it many different value add-on packages. So from the software and hardware that we add on to manage the system and to deliver capability to the science teams that Greg and Jeremy will talk about later, to the different programs that we have for education and outreach, which Scott will talk about, our industry partners, our Great Lakes Consortium for PETASCALE Computing, as well as our top flight application support that lets teams get the most out of the system and the environment. The system itself looks a little bit like this. We have a roughly 13 petaflop of peak computational capability. As I said, over 1.6 petabytes of memory. We have 26 petabytes of usable storage, with a sustained performance of over 1 terabyte per second. By the numbers to get a little more detail, that's delivered through over 26,000 compute nodes, actually over 27,000 total nodes in the system. The bulk of the system is a pure CPU system with 22,636 compute nodes. Those are dual processor AMD Opteron-based systems with interlogos processors, each with 32 integer cores. And we augment that with over 4,000 XK7 GPU compute nodes. So each of those sacrifices one of the interlogos processors for an AMD Kepler K20X GPU. And that makes us one of the largest, or actually the largest by far, GPU resource within the NSF portfolio. We augment that, as I've mentioned, with a top-notch storage subsystem, including data transfer nodes and data movement nodes for off-site, as well as a best-in-class cyber protection capability that lets us move that data over the external network without impeding flows, but still keep the cybersecurity aspect of the system very safe. As I mentioned, our network connectivity is best in class for any NSF center and indeed most any other HPC center around the world, with over 400 gigabits of connectivity between the University of Illinois network and to various connectivities within Chicago that lets us connect to both national and international research networks. The allocations on Blue Waters are really what sets us apart from programs such as Exceed. So NSF gets 80% of the system and regularly uses at least 80% of the system. That's allocated through a full peer-reviewed NSF proposal process. Typically, there are between 30 and 40 teams within that allocation at any one given point in time. We as the project do not directly participate in that review process, so we can give you advice, but that advice does not come from direct involvement in the process, only from what we see from past winners. Illinois, as the host of the system and contributing significantly to the system, gets 7% of the system with 30 to 40 teams in a biannual RFP. And the GLCPC gets 2% of the systems that they allocate through an annual RFP. Then there's the education allocation, which Scott will talk a bit more about later. That one has up to 1% of the system and can be used for a variety of purposes. Those applications are taken on a continuous basis, so Scott will talk about how to do that. We also have an allocation for our industry partners, both on an open published science basis or on a cost recovery basis. Then we have our innovation and exploration allocations, which allow teams that are doing novel science that's not ready for full scale out to bring it to the system and to get started on the system and explore whether the Blue Waters is a good match to deliver their computational science. And then finally, we have a new category called broadening participation that we intend to help bring underrepresented communities onto the large-scale computational science systems. And Scott will talk more about that near the end of the presentation. By discipline, we have a very wide variety of computational science domains that use the system. There are certainly some of the normal expected large-scale ones, such as the molecular biosciences, the earth sciences, stellar astronomy, and astrophysics. But we have a wide variety of smaller scale things, including things like social sciences and other areas that are less common there. So, and we do treat projects that are both very scalable. We have a job running actually at this moment on our system that's using all 22,600 of the XE compute nodes, which is a very impressive scalable feat. But we also have multiple projects that are actually not terribly scalable on an individual job basis, but they just have a very, very large number of jobs to run, such as the Arctic DEM project workload, which is producing a digital elevation map of the entire Arctic region. There they have individual single node jobs, but they run thousands of them at a time. So either of those extremes is a possible use of a large-scale system like Blue Waters. Indeed, some recent science highlights there include the Arctic digital elevation map, more traditional things like the tornado simulations and earthquake simulations, 160 million atom flu virus simulation, as well as being a part of the team that did confirmation of the LIGO binary black hole observations. So some of the other parts of the aspects to the Blue Waters project include an annual symposium where we bring together pretty much all of the Blue Waters project teams and PIs, and as well as graduate students and students that are involved in the science, to talk about their science and how they use Blue Waters, what they learned about using the systems, as well as interacting with the Blue Waters project team to identify ways that maybe we can help improve their efficiency on the system and allow them to make better use of their allocation in the future. The Blue Waters portal has pretty much a one-stop shop for all information about Blue Waters, from allocations to the user documentation. User support is there. We have a variety of methods of user support that are documented there, as well as more information about the Blue Water Symposium if you're interested in attending this year's symposium, which will be in June in Sun River, Oregon. I shouldn't end without talking about a follow-on system. Blue Waters is now 5 years old, and we expect to run until the end of March of 2019, with maybe a possibility for an extension past that, but that's the current plan. NSF does have a follow-on system funding opportunity that is currently under review at NSF. Proposals were due back at on November 20th of last year, so we do not have current information about the status of that other than it's under review. The RFP is listed at the URL there. That RFP seeks to deploy a system with 2 to 3 times the performance of Blue Waters and enter service by the end of September of 2019, which will be a tight time frame for a large-scale system like this. The RFP specifies that the NSF allocations of the PRAC proposal process will remain the same. The remaining 20% of the system will be determined through a cooperative agreement with NSF by the winning proposal team. And with that, I will now turn it over to Greg Bauer, who's our lead co-PI on the project, as well as our technical program manager for the application support team.
All right, thank you, Brett, and hi to everyone who's attending the webinar or viewing this later via YouTube. I'd just like to give you a brief overview of the Blue Waters architecture to help you understand how your science or engineering research can best utilize the system or benefit for some of the features that perhaps are unique to Blue Waters itself. So Brett already gave a high-level overview of the scale and scope of Blue Waters. It has a large number of CPU nodes and also GPU nodes. In fact, it has the largest, as Brett mentioned, the largest capacity and capability for a GPU cluster in the NSF portfolio at the moment. And unlike some other systems, it's stitched together or connected together by a high-speed interconnect that Cray designed a while ago. And that's probably what makes most Cray systems unique, is the proprietary network that is specially designed to provide low latency and high bandwidth for applications that need to scale out. So the Blue Waters network, which is based on a Gemini network interconnect, or router, sorry, that does provide low latency for strong scaling. That's probably one of our strong suits, where we can scale out applications to over 22,000 nodes or up to 700,000 tasks if you place an MPI rank on every core, or if you use some combination of MPI plus OpenMP or threading, for example. It's also able to sustain good weak scaling as well for some workloads where strong scaling isn't something that works too well. We have the capability with the 3D torus network of maintaining a very high aggregate bandwidth per node, as well as having ample memory per core to sustain the large memory footprint typical of most weak scaling efforts. So looking at some of the unique features Of the CPU nodes themselves, they are dual-socket AMD Interlagos processors. They've been around for a while, and AMD's had several generations go by since these were put on the market. They're kind of unique in that they have kind of a mixed view of cores and floating point units, where on Blue Waters we have 16 floating point units per node, but 32 cores per node. So 2 cores are able to direct instructions to 1 floating point unit. Each node has CPU node has 64 gigabytes of RAM typically, except for a small number where we recently, within the last year, doubled the amount of memory. So there are 96 nodes with 128 gigabytes. And that helps some applications where you might have a larger demand for one node where you are doing a mesh generation step and then distributing the mesh out to your compute nodes. So you might need a little extra memory. The memory bandwidth per node was quite good when the system was put out there. It was very competitive and is at 102 gigabytes per second per node, which is still pretty decent. Cray has put a lot of effort into providing a very low noise operating system for what they call their compute node Linux, which is very important for strong scaling. Allows you to scale out where you might have issues with synchronizing global tasks. And of course, we have good support for MPI, OpenMP, and threads and other programming models. The XK nodes on Blue Waters are on the same network, so that does allow for some unique workloads or development cases where you might be running your production workload on the CPUs while you're doing developmental work, porting your code over to the GPU. And also, if you happen to have a situation where you're able to do some very interesting load balancing, where you might run on the CPU nodes for part of your code and on the GPU nodes for the other part. So the XK nodes themselves have one AMD CPU, like we mentioned on the XE nodes, and one NVIDIA K20X, as Brett mentioned earlier, per node. So that's a fairly light balance. You might see other Linux clusters out there with 2, 4, or 8 GPUs per node. But at the time, to maintain high scalability and high communication capability with the system, Cray delivered these systems out there for our system and for such as Oak Ridge's Titan, 1 GPU per node. Each node has 32 gigabytes of memory typically, and like the XE nodes, we doubled the amount of memory for 96 nodes as well. So those could be utilized by some of the workloads like machine learning, where maybe you need a little bit larger memory footprint to get started. We do support several programming models for using the GPU: OpenCL, OpenACC, and CUDA. We're at CUDA 7.5 at the moment, although we're hoping that we might be able to move to CUDA 8. But at the moment, as of the time of this webinar, that's not in the roadmap. Our implementation does support CUDA MPS, the multi-process service, where you can have several tasks giving instructions to the GPU at one time on one node, and also support for RDMA message pipelining to the GPU from the network interface card. And of course, the GPU support is there for all the machine learning and visualization codes that use the GPUs. All right, we have a very rich software stack. This kind of is a bit of an eye chart, but it gives you a view of all the languages that we support, all the compilers that we support, Cray, Intel, PGI, GNU. We support many programming models, as I mentioned earlier. We have support for large-scale debugging. We have a broad suite of performance tools, I/O support, visualization support, which you'll hear about later, some other tools for development and for debugging as well, and of course your scientific library suite is very well supported by Cray as well. And it's a mix of vendor-supported libraries that are from third-party sources, and ones that we help provide access to as well. For many of you, Python is very important as part of your workflow, and we've responded to that. We've seen in the last 2 years a dramatic increase in the use of Python on Blue Waters, and as of last year, a survey showed roughly that 20% of Blue Waters users do use Python for part of their workload on Blue Waters. We have one of the largest packages of Python, or largest number of packages within our Python package, or our Python module on Blue Waters, over 260 packages and all the supporting libraries that are needed for those 260 Python packages. And we support both 2.7 at the moment still, and 3.x versions of Python. So that's a very unique feature of Blue Waters. We also, of course, provide support for GPUs through Python for machine learning, deep learning, et cetera. And also to keep the system current, as Brett said, the system is in its 5th year of operation. We've put a lot of effort into supporting containers, which allows newer applications that have slightly different software stack requirements that we may not be able to support with the native operating system on there, with a Docker-like container tool called Shifter, which we document on the portal. You can take a look at that. Some unique features: we do allow access to the MPI layer and the native driver for MPI, so you can have performant MPI within containers, and also access to the GPUs as well. And we are investigating, and probably will support soon, quite soon, Singularity as another Docker-like container on Blue Waters. We've also put a lot of effort recently in supporting data science workloads. We have a new data science lead within the Blue Waters project, and we are ramping up our support for all the available software products in there. Most of those are already available in our Python distribution, but we're doing a bit more detailed benchmarking, performance analysis of the different machine learning packages out there. And we're also trying to, as part of that benchmarking, we have been pulling down some of these large data sets that many researchers use when they're doing analysis of their algorithms, and so we're starting to make those available as well as a new feature for Blue Water. So if you're interested in doing algorithm development and you want access to some of these large data sets, we can help you with that by having them available already on our file system. Finally, since I'm part of the lead of the application support, we do have a good support model as part of Blue Waters. We do provide a lot of partner consulting with porting, debugging, working on your allocation issues, and dealing with software requests. We also look forward to working with teams on advanced application support, looking at improved scalability and overall performance, functionality. For example, for some teams, such as major science teams, the NSF PREC teams, we have points of contact, and we also look for other strategic projects where we also assign this point of contact model. We also provide support through other teams on workflows, data movement, and visualization. And you'll hear a bit more about visualization support in a minute. Just to give an overview of Blue Water staff expertise, most of these are in the application support team, but there is plenty of experience outside of the application support team as well. So we range from bioinformatics to computational chemistry and molecular dynamics, numerical methods and astrophysics, of course, and also the more traditional things with runtimes. We do, since we're located at the University of Illinois, we have several people who are experienced with Charm++ if you're interested in trying a different parallelization implementation. Einstein Toolkit for those of you who are doing astrophysics simulations, and of course we do performance analysis and programming model support as well. All right, so moving on, we'll now hand things over to Jeremy Enos, the lead of our operations of Blue Waters.
Hi, I'm Jeremy Enos, Systems Management Lead for Blue Waters. So I'm just going to talk a few words about how we operate the system. So I'll describe that in terms of our goals and policies a little bit, just a quick overview. One of our key goals is to make sure that the system is operating all the time at peak performance and as available as possible. I'll talk about our job scheduling policy, which is always of keen interest to our users. And then how we ensure best system utilization, and a few words about our appropriate use and security policies. So for performance testing and regression testing there, we have a large suite of regression tests to ensure that the system is always operating at peak performance and to detect any changes caused by any kind of configuration change, software upgrade, or any kind of hardware or performance issue that caused or even degraded. Blue Waters has unprecedented infrastructure for monitoring for a system of this type, and so we employ that extensively for investigation of any type of performance anomaly. Sometimes that's showing up as interference between users, which is something we want to minimize. In fact, we want to make sure that every user experience is as close to the feeling of an absolute dedicated system as possible, despite having some components of the system that are shared resources, like the network and file system that are shared components. We treat the system availability-wise much like a utility service. So we maintain 24-hour-a-day, 365 on-call staff to service the machine to make sure it's available. And we try and provide as much notice as possible for any kind of scheduled outages for maintenance where changes might be coming to the system in terms of software or hardware configuration changes. So job scheduling, this is definitely the area where users see what we do. One of the core tenets of our job scheduling policy is to not put any kind of arbitrary rules or constraints in place that are not there without a reason. So we want to retain the maximum job submission flexibility. In general, our scheduling policy favors large and capability jobs. Our queue structure is designed to be very simple, and we have high priority and normal and low priority queues, as well as a debug queue that's limited in time constraint, but as a high priority. We have fairness measures in place to prevent any kind of monopolization of the system or any resource by just a few. And of course, we want to minimize job turnaround time. We review this frequently for all classes of jobs. Speaking of flexibility, our minimum chargeable unit is 1 node, so any job can be submitted that uses as little as 1 node up to nearly 27,000 nodes all at the same time. So a lot of flexibility there. GPU and CPU node types are available. And we have the same charge factor for them, so that the charge factor is not a factor in selecting the appropriate node for the workload. Our maximum runtime allowed is 48 hours by default. We do occasionally serve special requests for longer runtimes. We also have special requests for advanced reservations, educational courses, escalated priority to make a deadline, and other types of reasons as well. So somewhat related to job scheduling is the utilization of the system. It's a large and expensive resource, and we want to take up many steps to make sure that it's used as efficiently as possible. So occasionally we will offer discounts on certain types of job submission that complement the idle system portions to make sure that we're using as much of the system as possible at all times. It is also a good utilization practice to do job placement according to the jobs communication and resource profile, so that we will place jobs differently and with different constraints based on their resource requirements for things like the network that are shared. We regularly review and observe the way jobs are being submitted, and if we find a user that is submitting jobs that are not the best efficiency for that particular user, we'll probably reach out and provide some guidance for best use to improve their efficiency as it also improves ours. We will also look into disruptive workflows since we do have shared resources and we want the system to feel like a dedicated system. On these shared resources, occasionally there's unintentional use of a shared resource that other users of the same system can detect as slowness, and so we use our heavy instrumentation and monitoring to investigate and diagnose those things. Sometimes those are reported as and manifest as inconsistent runtimes, and we want the system to be very predictable performance and very high performance at all times. So a few words about our security and appropriate use policies. We're very proud of our track record of perfect zero compromise record in terms of attackers. This is due to a multitude of contributions. One is a state-of-the-art intrusion detection system that employs keystroke logging of all activity on the system. It also has mandatory two-factor authentication. Our privilege model is hierarchical and unidirectional, and what I mean by that is that even if we were to publish keys to the system or administrative passwords, they would do an attacker no good, even if they had them. So our security team also monitors applications for appropriate use to ensure that our applications are spending time on the system towards the scientific purpose that that the system was allocated for. And then finally, we place an extreme priority on getting security patches deployed in a timely manner to mitigate any kind of vulnerabilities that do come up. So with that, I'll turn it over to Michelle Butler.
Hi, my name is Michelle Butler. I'm in charge of the storage systems here at NCSA, and I have just a few slides to talk about that. First of all, I'll talk about the online storage. This is the Luster file system that sits directly on the Blue Waters machine. The home file system has 2.2 petabytes usable and a terabyte user quota. The project file system has 2.2 petabytes also usable, and it has a 5 terabyte group quota. And then the Scratch file system is the large high-performance environment. It's 22 petabytes usable storage, and each group gets 500 usable terabytes there in their quota. Those are all adjustable. There's also some other environments that you can ask for a purge, 30-day purge policy to be exempt for your online work if that is required. So going back to the slide, it's a Crace and XTN Luster file system. It's viewable from all the compute nodes and the login file systems. It's also viewable to our data transfer nodes. There are 78 data transfer nodes to move data in and out of the Blue Water system, Nearline and online. The Scratch file system does have a 30-day purge policy that's in effect for both files and directories. So be careful of that if you have long-running files on that system. The Nearline system is capable, as like Brett was saying, is in the upper bounds of 200 petabytes in size. The home environment is 5 terabytes quota for each user, and then there's a project quota directory, and that's 50 terabytes for each group. It is accessible by Globus Online Go. There's a CLI or there's an interactive environment. And this is the long-term storage for the length of your project. After your project is over, the data is to be moved out and then moved on. If your project gets another one, if you get another allocation or something like that, we can help you move your data between those two. It's easy to move data in and out of Blue Waters. We have a lot of data mover systems that are dedicated just to move the data. This is the Globus Online. There's Globus Connect servers. They're very high bandwidth. The online system has 28 systems dedicated to move data out. Each one of those systems has a single 40 gigabit Ethernet link to the outside. There is also the Nearline system has 50 data movers, and each one of those has 2 40 gigabit Ethernet interfaces to move data in and out. And then I'll turn this over to Rob for scientific visualization.
Hi there, I'm Rob Cisneros, representing the group of Viz folks that works on Blue Waters. Our primary mission is to make sure that if visualization is needed by any science teams on Blue Waters, that we provide that. And so we do this through basic support of software and other basic tasks like training and preparing data, up to more complicated research tasks like trying to find or develop methods to show very specific features in data sets. And finally, we also do some creating pretty pictures for outreach and other things. Typically, what we expect when we're dealing with very large-scale data is that there's this data model where a data set will be broken into some number of subdomains. And so this is how we get data parallelism when we're running on a supercomputer. And as you can imagine, this creates issues with which pieces of software that are even applicable or which that we decide to support. Here is a current list. We support the specialized YT. Our general tools are Pair View and Visit. And then we also have other tools in the machine like IDL or ImageMagick. For more information on at least a couple of these pieces of software, there are webinars available on YouTube, and there will be a YT webinar on February 28th. So here's a little bit about YT. This was originally developed alongside an astrophysics simulation code. It was developed in Python, so if you have a Python workflow, it might be an excellent target for implementing some new functionality. And it also has batch and in situ support. And the lead developer for YT works at the university. Our typical tools for doing the distributed data parallel visualization are Visit and Pair View. And so I created a little Venn diagram here of showing the difference between Visit and Pair View. They're both very scalable, have client-server interactive mode, batch mode, in situ support, a rich set of data operators, and native file format support. And there's actually nothing worth putting outside of the intersection. And so quickly, I'll show a few examples of the types of visualizations we create with large-scale scientific data. Here are the 6 that came right from Visit's tutorial slides. So the top right, pseudocolor rendering, is sort of the bread and butter. It's a topologically 2D, 3D visualization, so you're only looking at the outside of the data set, so it's much faster to complete. The bottom left is volume rendering. It's much more intensive, but you get better results. And then there are also ways to look at vector data or flow data, molecular data, even categorical data. All right, and finally, I'd like to show one quick example of that I think illustrates well why this giant data is sometimes a huge headache to deal with. So this is a simulation run on Blue Waters. It is an AMR grid, so there are separate levels of refinement here, and the only thing anyone cares about is this little nugget down there. And so if you render that little nugget, it looks like this. And so this actual image is one that I created for a poster outside of our SC booth. And when you print this thing at 220 DPI, it's over 7 feet tall. And so the point here is that this little black box in the bottom of the visualization, there's enough data there to create an HD resolution image. So we always have this expectation that we can see everything that's interesting, but in our scales, that's not exactly the case.
Good morning, everyone. My name is Maxim Belkin. I'm an education and training coordinator with the Blue Waters project, and today I will talk about the Blue Waters training efforts. So first of all, let me state that our target audience is current and future Blue Waters users and partners. Our goals are to train new users that come to the system to better utilize Blue Waters resources, but also we would like to help advanced users basically find out new technologies and use them on Blue Waters. These technologies include things like HPC container solutions, machine and deep learning, and heterogeneous programming. Current offerings are Blue Waters webinars, which is you are participating right now. And Blue Waters webinars, they have various topics, applied topics such as scientific visualization tools or workflow tools. And there are also general topics. They can be informational and they can be also hands-on sessions. Our security team allowed us to basically perform hands-on activities on blue waters, and this is actually a very big thing for us. Please feel free to request or suggest a topic. We are open to suggestions. And keep in mind that this is a great opportunity to get publicity. Besides webinars, we also support partner training sessions and events, such as hackathons and distributed classrooms, for example, Exceed training. If you have any suggestions or needs, please feel free to send us an email at bw-eot@ncsa.illinois.edu. A couple of words about upcoming training sessions and events. First of all, we do plan to have a machine learning workshop very soon. There also will be training on containers in HPC, and the workshop will be actually on Shifter. In August, there will be a GPU hackathon, and we are currently working on training on Python in HPC. And with that, I'll turn it over to Scott.
Thank you, Max. So you heard from Brett earlier about some of our allocation categories. I want to focus on two. One is we have education allocations, for which you can apply anytime throughout the year. It's really to help support the preparation of the HPC workforce. Projects can be up to 1 year, although typically they're for 1 or 2 week workshops, institute seminars, but they can also be used to support classroom activities. So if you have a class working on it over the period of a semester, that's an appropriate type of usage as well. Nominally, request should be under 25,000 note hours, but if you have a very large class or you find that over time you need more, you can always request a supplement. So there are just a few examples of some of the types of projects. It could be focused on large-scale data sets, optimization of I/O operations, and so on and so forth. We encourage you to apply again throughout the year. But we do ask that you give us at least a month's notice so we can get the requests processed and allocations set up and accounts distributed. So we encourage you to take advantage of this. It's been a very popular resource for people across the country. We have a new allocation that we're opening up shortly. This will be open to faculty and researchers at U.S. academic institutions that have not previously had a Blue Waters allocation. The particular focus is to help encourage more underrepresented communities. This is a new initiative we're presenting to NSF as a prototype program that we hope will be supported and sustained well into the future. The guidelines for this program will be announced in the very near future, and since you're attending this webinar, you'll also receive information when that is available. So the target for this opportunity is for individuals at minority-serving institutions, institutions within upscore jurisdictions. We particularly want to encourage women, minorities, and people with disabilities as PIs for these requests, but also for fields of study that are traditionally underrepresented in the HPC communities, such as scholarly research in humanities, arts, and social sciences. Graduate students and undergraduate students are not eligible to apply. You need to work through your advisor, faculty member, etc. But you are welcome to include co-PIs and collaborators from other institutions. And again, it's really for first-time Blue Waters allocations PIs that have not previously had access to the system. Requests can be up to 200,000 note hours for 1 year. And the projects will be judged based on their scientific merit, the suitability for running on the Blue Water system, and the demonstrated need for the capabilities of the Blue Water system, which you've heard about in this webinar today. And there will be progress reports required for all the wards. This is really a new opportunity. We hope that many people in the community will take advantage of it to get the first foyer into using this such a large-scale system that you can then use as a stepping stone to larger allocations in the future. With that then, we'll give a quick brief summary of what you've heard during this webinar. The Blue Water system is an outstanding computing system, one of the largest installations of Cray's most advanced technology. You've heard about the extreme scale Lustre file system with advances in reliability and maintainability. It's a very balanced system for the open research community, capable of addressing science problems that can address memory, storage, compute, network intensive issues, or any combination of those above. Its use of innovative technologies, we believe, will provide a path for future systems. NCSA is a leader in developing and employing these technologies, as well as contributing to community efforts. With that, you can find general information about Blue Waters at the URL provided there. Assistance with any technical questions about the system, please contact that email address, help+bw@ncsa.illinois.edu. We look forward to your participation in taking advantage of the resources and services you've heard about today. And if you have any questions, don't hesitate to let us know. With that, that'll conclude today's presentation on the Blue Waters overview. If you have any questions, of course, please do contact us. I don't believe... We've had a couple, but we've answered them individually. They weren't of general interest.
Okay.
So if you do have a question, go ahead and post it. In the meantime, I will say a great appreciation of thanks to all the Blue Water staff who are here to help provide this presentation. We will let you know when the recording is posted on YouTube so you can view the recording. Next upcoming webinars next week, Aaron Saxton will talk about machine learning using TensorFlow. That'll be February 7th. And then Dan Katz will be talking about sustaining research software February 14th. With that then, we thank you for your participation and look forward to you at a future webinar.